Okay, good morning everybody. So today we will discuss, we start with this because we have discussed so far about the particulate characteristics. Yesterday, say Professor Chakravarti has started with fluid properties, but we are essentially dealing with solid in fluid in order to separate solid particles based on their physical properties. So, I would say that from a separation point of view in a fluid medium, it may not be always with water, it is the heart of this, basically the separation procedure. If I do not understand this, I do not understand any separator how it works. So, there is a bit of fundamental one, that is what are the physics behind it, but my focus will be more of a, that is what kind of models I should select for calculating some kind of your properties of the solids in fluids. Okay. So, to give you a broader say actually the areas of application of this topic, I would like to request you that just imagine your life without suspensions. Probably at one go you are not able to understand what I try to mean, but next slide I will try to show some of the examples, broad areas of applications of suspensions. Transportation of slurries in pipelines. What are the basic things? If I want to transport a material from one point to another point through a pipeline using a fluid medium, that particles should not settle. Otherwise, you cannot transport it. You will having difficulties. Okay. So, foods like your butters, pudding, sauces. When you have sauce, why there is an expiry date? What will happen to the sauce? Why? So, you will find that everything has settled, the particles, and you are having a solid liquid separation, but I do not want. Even the, so what I am trying to say that we are also essentially dealing with some kind of suspensions there. Okay. Look at pharmaceuticals, that is what we discussed one day, cough syrups, laxatives, shake well before use, shaking required to bring it into suspensions. Even look at our biological fluids, blood. Blood is also transporting particulates. We have got WBC, RBC and all this. I will show you in the next slide also, next to next slide. Household products like paints, printing inks, liquid waxes, coating suspensions, everything, there has to be a suspension. So, the essential thing is that particles should be in suspension, but how do I make them suspended if I do not know the physics of movement of solids in fluids. Personal care products, nail polish, lotions, creams, petroleum industry, I can keep giving examples, but our domain is mostly on mining applications and mineral slurries. Okay. So, we will come to that. Before that, I will try to show you what Professor Suman Chakravarti yesterday was talking about, pump and pipeline system. In processing industry, we need to have pump and pipeline system for slurry transportation mostly. How do I send my material from one unit to another unit? That is, we need a connecting tool, that is your pipelines. So, in the form of slurry, that means mixture of solid and fluid. I give this analogy to our processing plant with our human system. Even our human system, I will say it is a mineral processing system. Okay. If I look at, that is probably you remember my introductory lecture on mineral processing. Now, we are taking food. Okay. I can, in terms of processing industry, we call it feed, doing same thing, the feed to that system, that is our system, we are feeding our food. Okay. Now, what do we do? If I do not have teeth, if we do not crush them, so what will happen? That will be my choking will be there. So, now it is basically we are trying to liberate also, or we are trying to do size reduction with our teeth. And you see that our jaw, that is probably the name of jaw crusher has come from this. I do not know the history of that, but probably I am gassy. So we are doing same thing, but if you just say keep it in say in between your teeth, nothing will happen for a solid particle. You have to put pressure. How do you put pressure? One jaw is fixed and another jaw is moving. That is the same thing with the jaw crusher, that animation I have shown you. How far you will crush it? Up to a minimum size, then after that you don't need anything. That is what in a jaw crusher also we are doing. So that is what I am saying, that is your teeth, that is your crusher. And then you have got another filtration unit. What happens? You have got the tonsils here. The tonsils, what do? They further filter it. And there is a valve also. There are two domains, that is one goes to the your say your what I call it, say actually to transport your food material, another one is your supplying your exactly. So you have a air passage also. So if it goes to the wrong side, then also you are gone. That is your air passage will be choked. So how do I divert it? So there is some kind of your splitter is also there. That is your splitting mechanism is there. So if the splitting mechanism does not function properly, then also the system will choke and entire thing will go into wrong side. Then ultimately what is happening, that your food is coming to your digestive system. That is what we can call it as a slurry preparation system. Let's suppose I have to add some chemicals for my flotation process, and then I want to ensure that that is properly mixed. So normally we use a tank, we use your mixing mechanism so that they are properly suspended, and then they will be fed to a particulate separation unit. So that is called a slurry preparation unit. So our digestive system is also nothing but having an analogy to the digestive system, and here we add some kind of your chemicals in terms of what? In terms of some acids and sense of enzymes to help completing the process at the time what it should be. That is, we have fixed some residence time for particular type of material. So it is automatic, but this automation we want to bring it into our processing system also. That is our challenge. That is what we call it the modern plants and all this, but our body we have got an automatic system. And if there is a malfunctioning of any system, we have to go to the doctors. That is, they repair it. They are nothing but they are also engineers. They are playing with our human body, we are playing with machines. Okay. So it is also machine. Okay. Then what happens? Then you pump it. Material has to be transported. Some material will be transported because of gravity, that is fine. But what is my transporting channel? Is my arteries. All this. Where is the energy coming from? Professor Chakravarti said that you need to maintain a head. Head means you need to have a pump. So where is the pump? Pump is our heart. So that is basically pumping, and my channels are basically the arteries. Okay, that is through which I am flowing that. So if I understand this system properly, so if you want to understand slurry preparation, your entire pump pipeline designing system, that is why yesterday when Professor Chakravarti ended his course with giving you a problem that your designing of your pump and pipeline system, there is no fixed rule, you can have your own designs with some basic calculations. That is the project he has given you. So even he said that it is also valid for our human circulatory system, that is why he said this. Now if I understand this system properly, I can also design a pipeline system for my processing plant, for my petrochemical plant, for anything. Okay. So if someone is interested in biology, we will look at this system also, how they are being transported and all this. Okay. I leave it to you. Next one, if you look at our blood, blood is also basically a suspension. It is also transporting the particulates, RBC, WBC and so many BCs and other enzymes and all this, some form of particulates. Now what happens when you have this some kind of a chest pain and all this, then we go for kind of angiography or something, and then they say that there is blockage. What is blockage? Blockage means that this channel, basically I have got a diameter for this transportation. Now if the diameter is reduced, so what will happen? There will be pressure on that wall of that, and that wall can sustain a maximum limit of pressure. So beyond that, what will happen? It may burst. And another thing is that it may fail to supply my essential ingredients for my body at a rate what it should be. So I may be having some other problems, and to overcome this, what will happen? My heart will start working at a much higher rate than what it is designed for. So what will happen if it overworks? There is a possibility that it may fail. So I may not be having direct linkage, direct problem with the heart, but if there is some problem with my arteries, it affects my heart. So now what happens? What it could be? If the viscosity changes, then also my flowability could change. What are the viscosity? What are the reasons for viscosity changes? That's why they say some kind of fat, that they may change my viscosity. Okay? That is some type of cholesterol. Some cholesterols are good cholesterol, some cholesterols are bad cholesterol. That means they change my viscosity. What viscosity means is the resistance to flow. So when my resistance to flow is more, that means my heart has to work and more aggressively. So my life of my heart, that is a machine, will go down. So then again you have to seek the advice of a doctor. So normally the medicines, they start with viscosity modifiers. Okay? And then also if it doesn't work, that is your blood pressure, how it is going. Okay? So blood pressure is basically an indirect measure of your, what is the flowability of my blood and all this. Okay? Then if that doesn't work, then you go for some invasive techniques, that whether there is blockage or what kind of blockage. Then sometimes you may have to bypass. That is what I was saying, that okay, this channel from here to here, it is very difficult to repair it. Then let me bypass, we will have another channel. That is what also in our slurry preparation, slurry transportation system, many times we do. The plant people will agree with that. Okay? Anyway, so now I am coming to the slurry transportation thing. I have to transport my material around 500 kilometers, 700 kilometers. These days, Coal India is planning that we will double our production by 2020, it should be 1 billion ton. But I asked in one closed door meeting where railway people were there, NTPC people were there, and even Coal India people were there. I asked that very top person from railway, that is railway also gearing up for the transportation? Because when your production is doubled, who will transport the coal? Railway said, no, we don't have any plan. Then even if you produce, how you are going to send it, deliver it to your NTPC or your client store? So you have to find out alternative mode of transportation even. Now how you are going to transport 500 kilometers, 600 kilometers, and suppose the road and rail lines are not viable, then you have to think of pipeline transport or some alternative mode of transport. So in that case, if I want to transport, that they have to be in suspension, but how do I keep them in suspension? What should be the design of that? So essential feature for all this, the heart of this, that is what is the particulate behavior in a fluid, I must know. Otherwise I cannot start with even the calculations and even thinking of the designs and all this. Okay. So the stability of suspensions, many times it is not that I always want my particle to be in suspension. Many times I want them that how quickly they get settled, like your solid liquid separation cases. I want that my solid should be settled as fast as possible. But in any case, in both the cases I must know how solid behaves in a fluid medium. Are you convinced? So, this is what we are going to talk here, that is, our scheme is that in either case it is crucial to be able to predict the rate of settling, whether I want them to be settled or whether I want to keep them in suspension. This essential calculation, this essential understanding we must have. Okay. Now, this is influenced by a large number of variables. This is not as simple. Okay. So, what are those variables? We start with the general scenario. Okay. What influences them? Basically, the particle characteristics, of course, that is size, shape, orientation and density. Then what we are interested to know most of the time, what is the terminal velocity? We will talk about that, what is terminal velocity and all this. And then it is also, this is also influenced by your fluid properties. Fluid properties means what type of fluid it is. Like your sauces, okay, many times when you want to use, even if you have tilted it, even if you are putting pressure, you will find the sauce is not coming out. Many times in morning when you are dealing with the toothpaste, you will find that that is happening, it is not coming out, you know. Then what do you have to do? For sauces mostly it happens, you know, you have to do like this. What is that you are doing? It has got some residual stresses. So, that residual stresses you are basically overcoming, then only it will start flowing. That is the property of that particular fluid. It is called Bingham fluid. Okay. It has got the residual stresses. So, what kind of fluid it is? Now, if I want to do if my area of say your job or say something like to deal with sauces, then I cannot use the formulas what I use directly for your water, because whether it is Newtonian fluid, whether it is pseudoplastic fluid, whether it is viscoplastic fluid, please look at the textbook, we do not have the time to discuss all of them, but I must know the nature of my fluid, what sort of fluid. Okay. Then and at what temperature, because temperature also affects my fluid properties, viscosity and density and other properties also. Okay. Then I have to get this thing understand, I must know the operating conditions, what is the diameter of my channel, where it is settling. So, it is the wall effects. Like I give you a very simple example, suppose I have got a very thin tube and then I have got a particle that is going down, it will have different type of disturbances than a very big say suppose of this the room size, and I am having only one particle going down, there is hardly any effect by the side walls. So, that is called the wall effects. Flow field, what type of flow field it is, whether my fluid where it is settling, whether that is moving or that is static. If it is moving, that means if it is flowing, whether it is viscous flow, whether it is turbulent flow, whether it is transitional flow, what kind of flow it is, that will also disturb the settling behavior of my particle into that medium. So, I must know that. Then whether it is, then other effects, we will discuss what are other effects. Then hindered settling condition, hindered means whether it is very few particles or very large population of particles. We will discuss more on this, okay, what is hindered settling and all. So, to understand all this and to limit this discussion, that boundary conditions for this discussion, because this is a very vast subject, but I just want to give you the basic concepts what is there. And in light of this, we will discuss our separating equipments. Okay. I always look at my separating equipment based on this settling velocity. Okay. So, here the objective is to develop schemes to predict the settling velocity of a particle of known shape, known shape. So, I have cut short many things, you know. I have eliminated many difficulties. Known shape, size and density in a stagnant liquid. That is also another modification I have made when the fluid is not flowing of known properties. Now, outline of this presentation, I will deal with spherical particles, also briefly deal with non-spherical particles, then concentrated systems. Okay. I will not be dealing with the very fundamental physics, but I will deal with only that much of physics which is essential for me to understand, to select a particular model or what I should do in my plant conditions and all this. So, this is more of a industrial application oriented selection or discussion of this on this topic. Okay. Now, I start with very basics. Suppose I have got a steel liquid and I have got a spherical particle and I let it allow to move into that. So, what will be the forces acting on it? There will be three forces acting on that. That is, one is your gravitational force field working on downward direction, and there will be the buoyancy force going upward. Buoyancy coming from where? What is buoyancy? Due to the displacement of the fluid in a pressure gradient, okay, because it will displace the equal volume of fluid. So, there will be a pressure gradient cause. So, there will be a force for that. So, that is called the buoyancy force. This is much more complicated, that is another force, that is called drag force. It is due to the relative movement of the, because it will be displacing the fluid, but the fluid is having a upward direction and particle is going in the downward direction. So, there are two layers and I have a friction. So, it is nothing but that is the frictional component of that. So, that nature of that friction will depend on my particle characteristic, how big is the particle, what type of, what density it is, because my how much of fluid will be displaced, that will be a function of that. And then if the particle is moving at a very faster rate downwards, the fluid also try to go up at a very faster rate. So, I will have a different type of frictions. Okay. If the two vehicles are hitting each other from opposite direction at a different speed, then your nature of your say actually degree of fatalities are different. But here you are not, there is no collision, but there is a shear. So, your drag force, nature of drag force will be different. So, I must know, so this is a function of my flow conditions, okay, that I will come. Now, if I want to put a mathematical equation, if I want to write it in the equation of motion of a particle moving into that fluid, I can write m is the mass of that particle, dv by dt is the acceleration term. It is basically again the p is equal to mf, okay. That is mass into acceleration is equal to the all the forces, okay. So, it is mf is dv by dt and mg is the gravitational component going down, its plus and minus, these positive and negative signs are given for showing their direction of movement also, okay. So, and minus mg, that is your buoyancy component, how much it will be? That is a function of your fluid density and particle density, okay. So, minus this CD, this is called drag coefficient. That is, how do I measure the drag? And for that I need that your friction, that is nothing but your friction coefficient. But in this case we call it drag coefficient. Drag is also various type, but I am not going into that detail, you know. the chemical engineers probably have gone through much more detail, but as I said, for my application point of view, how much I think I must know to start with, and this rho f is the fluid density, v is the particle velocity, a is the projected area of that particle. I am not saying is the size. Projected area means if my bottle, if it is going in this direction, what is this area in contact with my water? So, that is my most important thing. Okay? That is what is causing my drag and all this. But if it is oriented like this, then this dimension is the projected area of that. So, it is a function of your basically the orientation also. Now, if we simplify it, say suppose that dV by dt, what happens, I show my in my lecture in gravity concentration, that how much of time it takes normally. So, what happens when a particle starts moving into fluid medium, it normally has got some accelerating velocity following that first equation, but after a certain time it reaches a steady state, and that is called the terminal settling velocity. So, if we deal with this terminal condition and how much time it takes to reach that, that I will show you in my density separation or say lecture, because there is a reason for that. So, suppose if I simplify it, that I will consider only about the terminal settling velocity. So, I can easily put dV by dt is equal to 0, and if I rearrange it, because I want to know what is the velocity of this particle, that is what I am interested to calculate. Okay. So, that velocity now I have given a suffix of t, t stands for terminal. So, if you rearrange it, you will get Vt square is equal to 2 mg rho p minus rho f divided by Cd rho p rho f a. Now, if I know the particle characteristics and the fluid characteristics, I can always get the values for m, g we all know, rho p, rho f, and then a also, if I know the surface area, or maybe I am having some kind, suppose it is a spherical particle, I know the projected area remains unchanged, but Cd, where from I will know, that is the drag coefficient. So, this is neither a fluid property nor a solid property, that is a property, that is a basically your coefficient frictional force, frictional component. So, it is basically interaction between the relative movement of the particle and the fluid. So, how do I know it? So, that is the basically the challenge here, to know the Cd, that is the drag coefficient. Now, you see that what happens. So, spherical particle, I can write m is equal to pi dp cube, that is dp is the diameter of that, then your rho p divided by 6, I am just is basically volume into density. If it is a spherical particle, I am assigning that value, and for your area, projected area, it remains unchanged, I can give a value of this surface area. Okay. Then if I put these values into that equation, I can get a form like this, Bt is equal to 4 dp g rho p minus rho f divided by 3 Cd rho f to the power 0.5, that is square root of this. You all know probably up to this. Okay. So, that is the general formula for a spherical particle we get. Now, again the Cd is basically, say I have got only one equation and I have got two unknown. I want to know Vt, but for that I must know Cd. So, how do I solve? So, I cannot solve, mathematically it is not possible. So, that is the challenge, how do we find Cd? Now, as I said, the drag coefficient is what? It is basically the relative movement of my particle and fluid. I give this example to you, that suppose I have got a water body, and if I dip if I throw a very little particle into that water body? Will it disturb the entire water body? Will you be able to see any wave coming or something like that? It will just dip, isn't it? But if I have a very big rock mass and if I am throwing it there, what will happen? The entire water body will be disturbed, there will be splashing and everything. So, what it, say actually why it has happened? Why the small particle did not create any disturbance, even it is not noticeable, but the bigger particle will draw the attention of everyone who is nearby, something happened. So, so the nature of the disturbances into the fluid medium is also dependent on the nature of particle you have put into the system, isn't it? So, when you have dropped a very big particle, the splashes and in all different directions, can you predict it in mathematical terms? That is nothing but a turbulent conditions. Okay. So, what type of CD will be there? So, that is also dependent on what type of particle you are dealing with and what type of fluid motion it has created. So, it is a relative. Now, how do I quantify it? How do I quantify it in mathematical term? That is where basically the Reynolds number coming into picture. What is Reynolds number? Please do not tell me rho v d by mu. There are many other forms to express Reynolds number. What essentially concept wise Reynolds number is? It is the ratio of inertial stresses and viscous stresses. So, what happens when Reynolds number is very less means your viscous component is much more higher than your inertial stresses. So, that is why we call it is a viscous flow. When Reynolds number is very high, that means your inertial stresses are dominant, viscous stresses are negligible, that is why we call it turbulent flow. But to put a number on that, that is what Professor Chakraborty was telling, that do not tell at 2000 to 4000 will be this, above 4000 will be this, no. So, that depends on many other factors also, many times we have to measure that or maybe track that what is happening. So, whatever in the literature we get, that is based on some Parsons, say your controlled experiments we are getting. Okay. So, it may not be always true that you put a number, okay, on that. But there are some normal criteria who have done experiments. So, again it is coming to the experiment word. Fluid mechanics, this physics, when you want to apply it, you will just see that 95% depends on empiricism. You start with very basic Navier-Stokes and all this, but you try to solve those problems, you try to solve Navier-Stokes for a particular system, you have to bring empiricism, you have to bring empirical models. Okay. So, it is basically the engineering of this nature requires empiricism. We have not say our science or understanding of the subject has not gone beyond a certain limit. Okay. So, drag coefficient depends on flow conditions around the particle, that is the Reynolds number. Of course, we can express it as Vt rho f dp by mu f. Vt is the again terminal settling velocity. Now, that is what I am interested to know. Vt I am interested to know by again Reynolds number I have introduced, but that is also having that component Vt. So, I cannot also solve with that. Okay. And rho f is the fluid density, dp is the particle size. Now, the fluid property is coming, that is the viscosity of the fluid. When viscosity of the fluid I am talking and the density of the fluid I am talking, I must talk about the temperature of that fluid. So, that also changes. Okay. So, I must describe all these conditions. But some of our say very well renowned scientists, they have eased our problem a bit because of their research and findings which are in the textbook. So, you all are familiar with Stokes. You know, in our IIT Kharagpur there are at least 6, 7 or maybe more than 6 professors who are working on Stokes flow, mostly the mathematics department fellow. Even that what is Stokes, nature of the Stokesian flows and all that is their research area. So, the Stokes we are simplifying it for application point of view, but it is not that simple. So, Stokes or laminar region we say. Now, if you look at different textbooks, different journal articles, there is enough scope to be confused with this number. If RE less than 0.1, I have seen many journal articles, they say if RE less than 2, RE less than 0.2 is very common, RE less than 1 is also very common. So, what RE limit I will take? Because if RE is less, that means if Reynolds number is less than 0.1, why it is important? Because the Reynolds number is coming from your particle properties. Fluid property is almost constant, is fine because it is a static fluid, but the size, density, shape, it takes care of everything. Rho V d mu, what is rho? Rho is the density of that particle and the d is the size of that particle, isn't it? So, for this discussion purpose, let us accept this, that we will go by this Reynolds number less than 0.1. Then the Stokes recommendation was that CD is equal to 24 by RE. That is an empirically derived formula. People may argue, but that I can show you after 2-3 slides that now people are not even accepting 24 by RE. They are now saying it is 24 by RE plus 0.116. Then it is empirically derived. Then if it is analytical solution, then why you should have arguments? If someone is interested, look at the original papers, but they are very old papers. That is what I said, many people are still continuing research in this, that is a very vibrant research area. So, now for this, if I take CD is equal to 24 by RE, now if you have noted down the final formula, that is this formula, please note it down. Now, here if I put CD is equal to 24 by RE, that means 24 by rho V d by mu. So, then I can get to know all the values. Okay. So, what will happen in that case? I get a Vt is equal to G dp square rho p minus rho f divided by 18 mu f. So, please derive all these steps if you are not familiar with this, but many people are maybe getting bored in this audience because I have started with very basics and they are doing research say at a much higher level, but I know the background of the people. So, for some people it may be the new thing, for some persons it may be very basics. Okay. So, now I can calculate. So, but there is a condition, if the Reynolds number is less than 0.1, then only this equation is valid. Now, I can calculate everything because every parameter I know. Okay. But in terms of particle size and density, what is that Reynolds number less than 0.1 means? Okay. Now, this is what basically if I have a, so I have to mention, when I am mentioning size, I have to mention the density, or if I am fixing the size, then otherwise I have to fix the size to know the density. Okay. So, it is called the quartz density particle. That means it is 2650 kg per meter cube. So, if I am dealing with a quartz density particle, that is a quartz particle, then Reynolds number less than 0.1 is applicable to a particle size less than equal to 50 micron. Are you getting there what I am saying? So, when I can use Stokes law, that is what I am trying to tell you. I cannot just arbitrarily use Stokes law. Stokes law is valid for only viscous flow. Now, viscous flow, that is a Reynolds number range, that is a 0.1. That is why I said many textbook I have seen, many articles, they even deal with Reynolds number 2. So, when you are increasing the limit, you are increasing the size limit also. But majority of the people, they accept Reynolds number 0.1. Okay. So, it may happen also for Reynolds number up to 2 also it may be Stokesian flow, but then you have to do the experiments, you have to look at whether really it is streamline flow or not, and that you have to prove first. Okay. So, if I have a particle having density of 2650 kg per meter cube, I can apply this equation if my particle size is less than or equal to 50 micron. Now, if it is gold, now if it is gold density particle, what will happen? What is the gold density? It is around 19,300 kg per meter cube. So, when my density is more, remember Reynolds number is equal to rho V d by mu, sorry. So, rho is more in this case, so my d will be much smaller. So, it will be much smaller, that is what the calculations as an assignment I will give you, or maybe in the exam I will give you, and that I can easily calculate it from this equation, is not it? Now, if I say that a gold particle and a 50 micron quartz particle are having equal settling velocity, that means they are having identical velocity into a say still fluid, what is the size of the gold particle? Unless and until we calculate it, it is very difficult to tell, but I guess it will be around say 15 to 18 micron. So, that means if I am dealing with gold, but I am not sure, I have to calculate it. I cannot say that okay, SAT said less than 50 micron it will be Stokes, no, it is for quartz density particle. Now, you are dealing with gold particle. Now, if it is coal, coal density is less than this. So, from my sink float analysis, if I want to know what is the settling velocity of this particle group, now say suppose that is 1500 kg per meter cube of those particles, then I can calculate. So, this will be coarser than this, but how coarse? For that I have to calculate this. These are the applications. Okay. That is where I can select, but normally we are being taught Stokes law, use Stokes law. No, arbitrarily you cannot use the Stokes law. You have to first prove what sort of particles and all this. So, now that is for Reynolds number less than 0.1, that is for quartz density it is 50 micron. There is another scientist, probably you have heard. Who has not heard his name? Please raise your hand. This next gentleman's name, Newton. So, this scientist, he said, it is also his experiments and all this. Actually, this is the consequence, this is the coincidence, or many times when I am listening to someone, the lecture, that is why I said at the beginning that you must know my background, that from what perspective I am giving these lectures. You must know the background of a person, okay, when you are listening to him. So, the background of Stokes was that why he was basically interested only this very fine size range. Most probably he was working in a pharmaceutical company. A pharmaceutical company, you deal with very small particles, you do not deal with very large particles, and that was his requirement to solve his problems. So, he dealt with that, and this may be a byproduct of that, that you have come out with this type of relationship. Now, Newton probably was working on a very large particles. So, when he worked on that, he was seeing that no, Stokes equation is not valid. So, then he showed by derivation, by experiments and all this, that if my Reynolds number, the particle is greater than 750, then CD does not depend on the Reynolds number, your Reynolds number. Okay. So, CD has no correlation, it is a constant value, and he proposed the value is 0.445. You will be surprised to know that there are a lot of articles these days, even I have seen at least more than 50 articles on this about this constant. People are saying no, this 0.445 is not correct, it should be 0.441. So, it's a 3-digit correction changes a lot in your calculations, because your say suppose residence time in a system I want to calculate, and if I give this value, my residence time is coming say suppose 10 minutes, and if I make a correction of 3 digit 0.441, and that becomes 9.5 minutes or maybe 10.5 minutes. So, it changes a lot with my capacity and with my design and everything, it changes. So, that is why it is very important, but we are not doing research on this. Okay. So, there are even ambiguities on that, there are some doubts, but the range is generally 0.445, but you know, for our discussion purposes, for the textbook type of purposes, we always further simplify it. We assume that this value is very close to 0.5. Okay. We do not say is equal to, but very close to 0.5, and we put this value into that basic equation, and we write V t is equivalent to, you get this form. Are you getting there? So, I am not even using 0.445, there is argument about the third decimal point, but for discussion purposes we have simplified it to, we have assumed it to 0.5 for mathematical convenience. Okay. So, that is why we are writing this. So, is 3 d p g rho p minus rho f divided by rho f square root of that. So, now we have got two models by two reputed scientists, okay, Stokes, but you see the range. So, I have got a value for Reynolds number less than 0.1, I have got a model for Reynolds number more than 750. Now, what is the Reynolds number 750 means in terms of particle size? Again, for quartz density particle, this for quartz density particle, the Newton size is 5 millimeter. Okay. So, 5 millimeter or coarser than that normally in general. Okay. So, if you calculate that range Reynolds number, you will find that it is more than 750. It depends on fluids and all this. So, we have got a model for less than 50 micron and greater than 5 millimeter. But most of the cases, that is the examples I have given in the second slide, that is your or most of the suspensions and all this, you know, even in our mineral processing cases, fine particle processing, basically the problematic area, because below 50 micron we happily say these are slimes, put a desliming in it, let it take it out, let it go out of the system, do not deal with that. So, we are essentially dealing with major engineering applications are in between 5 millimeter to 50 micron. So, which equation I will use for that, and that is the challenge. That is why the focal point of this discussion, because otherwise everywhere you get the Stokes equation and Newton's equation in any textbook, and that is where little bit of my contribution is there also. And I have got, that is the review I made, okay, that is which model I should use. Even for this we call it transitional range. Many different people use different even models, Even I had lot of debate with Professor Eric that why do you use that, he has got some logic, but I am not convinced. I said no, I am not convinced. Now let me discuss my point, that is how we should do it, and it is all published, people are using it. So transitional region, how do I do it? So there are many single equation proposed for this transitional region. Great people worked on that, many. So Lappel and Shepard, and these are mostly flooded with, the literature is flooded with the chemical engineering people, chemical engineers, and they are all renowned chemical engineers, like editors of chemical engineering science or chemical engineering journal, or they are stalwarts. Okay. So this Lappel and Shepard propose a drag curve, that there are problems because what is happening, many people they were publishing articles saying that for my system this is the relation between drag coefficient and Reynolds number. These two famous chemical engineers, what they did, they first rigorously examined the experimental setup. These are all measurements, not much theory is there. Whose experimental setup is believable, reliable, and experimental data set, and then they combined everything and then they plotted in the form of this, that is your particle Reynolds number versus drag coefficient. This is just a review. This is what I say the literature review means. The literature review should be like this. Okay? That is, they come out with some kind of your new things by. So when I say that if I want to do research, the greatest tool we have, that is our databases, and it is Wi-Fi enabled, the entire campus. Anywhere I hook up with my internet, I can get to know the Web of Science, Science Direct, or whatever journal I want. So I am moving with the entire library with me. What else I need if I want to do research? Even if I sit in the corridor, I can do research by looking at the journal articles, and if I have a thought process, I can analyze those data, the published data, and I can develop a model. Why I have to generate my own data? So many times I ask myself, and more than 40% of my publications you will find that they are like that, conceptual, based on the literature data, and I have disagreement with this and I have written that. So 40% of my publications are like that, based on concepts and based on arguments and this type. I am not saying that, I am not claiming of that level, this is all in the very high level work. So what they did, they plotted the, when they have say plotted all this data, I have got a typical shape of a curve like this, and now they named it drag curve. But now the entire community, that is community means the greater community who deal with this suspensions, that is solid fluid movements, they have accepted it. Yes, this is the standard. There is no point in repeating the test what others have done it much more accurately. Why do you spend money and time on that? Let us accept it for industrial application point of view. Whoever wants to do fundamental research, let them do it. So generally in engineering discipline, engineering application point of view, we have accepted it, that is the scientific community, we named it standard drag curve. Now if you are good at your curve fitting, or if you like some kind of your say curve fitting type of exercises you want to do, you want to write some code on that and try to get a single equation for this curve, give it a try. And I promise you that if you can give me a single equation to explain the nature of this car, I think we can publish it in very, very high quality journal, that I assure you. But many people have tried it, okay. They have proposed it. So now the condition is that if I have a single equation to describe the entire pattern of this curve, then I can put it into that my basic equation of motion, I can get a solution for the entire Reynolds number range starting from Stokesian to Newtonians. Okay. So that is what people have tried. Who are the people? Levenspiel, the same Levenspiel's book which you study in chemical engineering. These people I do not know who are familiar. Hyder and Levenspiel, Turton and Clark, that is also very famous chemical engineers. Have you heard their name? Clement, Concha and Almendra. Concha, Professor Concha is from University of Concepcion, Chile. He is a very famous professor in our mineral processing. I will tell you these two professors' name. He knows one. One is Professor Chabra from IIT Kanpur. He is in chemical engineering department, and some of my initial slides I have borrowed it from him. Okay, I said that these are very good slides to teach. Why don't you give me this human circulatory systems and all this? They said, okay, no problem, you take. So this Professor Chabra and this Professor Concha of Chile, both of them are very famous professors in chemical engineering, and they have spent their entire lifetime. They are now approaching probably 68 to 70 years. Okay. They have produced more than 30 PhDs. I know both of them personally. And all of his students, they have worked on some aspect of this settling velocity. And at the end, I will show you still where we are. I am not saying it is their failure, but it is how complicated this is. Okay. It is not very easy to solve. Okay. So now this Professor Concha, that Almendra is a student, PhD student, he published, I remember 18 or 19 articles on a series on your settling velocity. They are published in International Journal of Mineral Processing as a series. Okay. So this paper, this Concha and Almendra's paper, 1979's paper, now many of the softwares which are being used in mineral processing and coal processing, they are using it because a single equation very easy if I have for the settling velocity which covers the entire range. But I will now bring my opinion on that. I am not challenging, I am just giving another opinion that all these famous people they have done, but I would say that I am not going to select my model based on the tag associated with that person who has proposed it, rather I will go by the scientific manner. So, I will accept that model which can predict that drag curve closely as possible. That should be my basis of selecting my model. If I am developing a software and if I think that for my designing purposes, for my software development purposes, settling velocity plays a major role. If you are developing a model or designing the separation process, this has to be the first criteria, the settling velocity. And for that my accurate prediction as accurate as possible is essential. So, for that my guiding tool will be that look at the basic model what they have used for using the CD and RE correlations and plot it into an Excel and see that whether it can match the standard drag curve properly or not. That should be the selection criteria. That is what I did. So, when I looked at Concha and Almendra's paper, they have taken this CD and RE correlation from Professor Abraham's initial paper, the model, and Professor Abraham is a professor of MIT, and think that you see that what level of people are working in this field because of vast engineering applications for this basic phenomena. And when I looked at Professor Abraham's basic equation, that is how you do cross referencing. How many of you have read a single say research article, the students I am asking, how many of you have gone through a single research article? Have you? You must learn how to read a research article, how to get hold of a research article, otherwise you won't get to know what is happening, what are the developments in your field. Okay? You must make it a habit to go through the research articles. Books are okay for basics, but if you want to know that what is happening. So, here the Abrams model, when I have plotted, I have seen that it may not be visible here, that there is some, it is not getting exactly superimposed even in the Stokesian regions, and you see that this region it is getting almost superimposed, but it fails to bring this shape, typical shape. So, I was not very much convinced even with this, because here even I said that third decimal point disagreement can bring lot of differences in your predictions, and that has got huge effect on your processes. So, I was looking for a better model, that whether this is the best available model we have. If that is there, then I have to use it. I am not working on developing a new model, because otherwise I have to do a PhD on that. That is not my intention. My intention was to select the best available model for predicting the particle settling velocities. Okay. Now, what I did, there is a classic book by these three famous chemical engineers by Clift, Grace and Weber. In 1978, they published this book that is on bubbles, drops and particles. They deal with a very thin book, but excellent book, classic book. Okay. So, there I have seen that it has given, probably the equations, yes, it should, that graph should have come next, okay, the sequence problem. That what they have done, they have given this set of equations for the drag curve, the standard drag curve, that these are probably the basis of that standard drag curve. They are not very sure, but they said these are the best possible correlations. They have digged out from the literature, some of the correlations are their work also, that for different Reynolds number region you have got different correlation. Do not get scared, this is a very simple empirical equations. Okay? You do not have to remember this. So, it says that if Re less than equal to 0.01, now the Stokes region has gone to 0.01 from 0.1. Okay? They have suggested that better we use the Re less than 0.01. Now, see that how much of disagreements are there. It is not disagreement, it is what Professor Chakraborty was telling, that it varies from system to system. You cannot fix a number, but in general what do you use, you can talk. Okay? But if you are very specific, so to be safe they say that Re less than 0.01, then CD is equal to not 24 by Re, the 3 by 16 they have added another constant. Okay? Like that, you see that up to 10 to the power 6, huge range, all range covered, and they have given all the equations, and these are very simple equations, 24 by Re and all this. Then there is a factor of W, and W is log 10 Re. These are very simple, looks ugly, but when you look at closely, that they are not very difficult to solve, you know, it is very simple straightforward equations. When I looked at it, then I plotted it into this comparison of this drag curve. I find that at least it can bring the shape, and it is basically getting almost superimposed on that. And I searched the literature, I said that at one point of time I was having almost all the articles available on this topic. I could not see a better model which can fit this drag curve much better than this. So, I said that no, I have to use this set of equations for my settling velocity model, because that will be the heart of that my model. Now, question is, again if you look at that each relation CD and Re, So, my primary aim is to solve Vt, terminal settling velocity, for which I want to know Cd. To know Cd, that is again it is a function of Re, Re is again a function of Vt, rho Vd. So, coming into loop, I am not getting a solution. So, I cannot use them to solve directly even, is not it? So, how do I solve? Then I was looking at literature, fluid mechanics literature, is there any constant available which can predict this, some kind of I came across this, I am not going into detail that what is the implication of this, but there is another number that is best is the name of the scientist, best number that is being applied for some other purposes. The best number that is written in the form of this 4 rho f rho s is the solid density minus rho f g dpq by 3 mu square. And if I convert it in terms of Cd and to Re, it is also equal to Cd into Re square. Are you getting that what I am saying? That best number I can also represent in terms of Cd into Re square, as well as the best number I can directly calculate from my material and my fluid properties, because these are all known, there is nothing unknown. So, then I thought that why do not I use this, because now I have got two sets of information, and if I write a small algorithm I can solve it. And for algorithm, once you have written a code, if it is correct, then you forget, because you have to just give the input data. What is the problem? Okay. Even in our softwares, you can say that is a function of that, and you can get a library function and can make it a library function and you can use it. There is no problem. So, how do I use it? So, what did I do? I wrote a small code. This is all published. This is getting very frequently referred. Okay. But I published it in Institution of Engineers Journal, so that my people, I wrote in that article that I am publishing it for the benefit of our industry people. I do not know how many of our Indian industry people they are using it or they are aware of, but I am getting to know that many people in other industries in abroad, they are using it. They write to me that it is excellent one, we are getting much better results even in designing and all this. So, flowchart for MATLAB codes. So, what I have to do? First I have to know the particle properties. So, enter particle properties and operating temperature. Why? Now, because the fluid density and viscosity is a function of temperature. Then calculate fluid density, viscosity and best number, because if I know all this I can calculate the best number. Okay. Now, what I can do, that is, now if I come here, now if I come to that iteration type of method, how many of you solve equation by process of iteration? You have taken a course on numerical analysis, have you done any say little bit of coding on that? Okay. So, what we can do that, because Re I want to know or Cd I want to know, okay, for that. So, if I assume a value of say Re like this, that is Re is 0.00001, then there is a range. So, then I can write a code that it belongs to which group, then directly it can go to that relationship. So, I can calculate a Cd value for that. Are you getting there? So, I will give an initial value of Re, and that Cd and Re correlation can be selected based on this set of correlations, that which group it is falling. Then I will also get to calculate the Cd. So, immediately I can calculate Cd into Re square, is not it? Now, I have got the best number calculated based on my input data, that is my material characteristic, that is size, density and the fluid density and viscosity, and my approximation is that if Re is equal to 0.00001, then what will be my Cd? So, I am also calculating Cd into Re square. So, if that assumption is correct, then the difference between these two should be close to 0. Are you getting there? Then my difference between the real value of best number and this calculated value based on the approximated value approximation that should be close to 0. So, that is my logic, that is what I said, that is pull small initial value of RE, calculate drag coefficient, that is CD, calculate best number again, that is based on the first equation, best number convergence you check. If my approximated value of RE is correct, then my CD into RE square and the calculated value of this best number, that difference should be as minimum as possible. But for computational safety, for time say saving purposes, you do not put equal to 0, but you say 0.00000. You all know, whoever has done programming. Okay. So, now if it is yes, so finish iteration and get the value of drag coefficient. Once you get the drag coefficient value, I can just hook it up into the basic equation. I can get the value for my Vt, even I will get to know the Reynolds number also, everything is known. So, that is how we can calculate. So, we have to take a break. Okay.